digital representation of a physical object or system. This is done using mathematical formula to describe the object shape, size, and other geometric properties. Geometric models are used in a wide variety of applications, including engineering, design, manufacturing, and entertainment. Computer geometric modeling is a computer representation of an object's geometry using software. Computer geometric modeling uses curves to control the object's surfaces as they are easy to manipulate. The curves may be constructed using analytic functions, a set of points, or other curves and surfaces. There are a number of software programs that then allow the mathematical description of the object to be displayed as an image on the monitor. A geometric model of an object can be created using these three steps. First is create a basic geometric object using the commands like points, lines, and circles in CAD software. So CAD is a computer-aided design, the use of computers to aid in the creation of modification, analysis, or optimization of a design. Second is use commands like achieve scaling, rotation, to transform these geometric elements, and third is to integrate the various elements of the object to form the final geometric model. So I will give you a bit history of this. So in engineering, modeling refers to the way data are represented in the computer memory and the way in which it visualized. The data is stored in suitable data structure that is easy to access for the visualization algorithm. Geometric modeling is the process of capturing the properties of an object or a system using mathematical formula. Computer geometric modeling is the field that discusses the mathematical methods behind the modeling of realistic objects for computer graphics and computer-aided design. It uses computers to store the data and the geometric properties of a system. It's relatively new technology that has expanded rapidly thanks to advances in the computer technology. The first generation CAD program of the 50s were almost non-interactive. CAD users were required to create program codes to generate the desired 2D geometric shapes. Interactive CAD programs began to take shape in 60s and were mostly used in the automotive and the aerospace industry. The 60s also marked the beginning of the development of finite element analysis methods for computer stress analysis and count for generating machine tool paths. The advent of microprocessors in late 70s boosted computer power of the computers. It also triggered the development of 3D CAD programs that were user-friendly and most importantly interactive. The 80s saw the expansion of computer application software technology from every simple computer-aided drafting to very complex computer-aided design. It was at this time that 2D and 3D wireframes were introduced in the industry of geometric modeling as a tool to increase productivity. During the process of geometric modeling, the computer converts various commands given from within the CAD software into mathematical models, stores them as files, and finally displays them as an image. The geometric models created by the designer can open at any time for reviewing, editing, or analysis. So CAD really came on its own with the introduction of 3D solid modeling technology which boosted the usage of CAE technology and in industry. The development of 3D modeling schemes started with 3D frames. It was a major leap in computer geometric modeling as it allowed designers to use a single object and view it from multiple angles. However, wireframes are susceptible to ambiguity because the surface definition is not part of 3D wireframe model. To overcome this lacuna, computer geometric modeling with surface definitions was the next logical step forward. With enhanced computer CPU power, the next enhancement in geometric modeling was solid modeling. So, surface modeling organizes and groups edges to define polygonal surfaces, making it easier for designers to visualize an object. So, the history of geometric modeling can be traced back to the ancient Greeks, who developed sophisticated mathematical methods for representing and manipulating geometric shapes. However, it was not until the advent of computers in the 20th century that geometric modeling became a practical tool for engineers and designers. So this is the early developments. In the 1950s, early computer graphic systems were developed that allowed users to create and display geometric model on a screen. These systems were typically used for simple two-dimensional drawings, but by the 1960s, three-dimensional modeling capabilities began to emerge. In the 1970s, the first commercial CAD systems were introduced. CAD systems revolutionized the way that products are designed and manufactured. They allowed engineers and designers to create and modify geometric models quickly and easily, and to simulate as well. In the 1980s, solid modeling became the dominant form of geometric modeling. Solid models represent objects as three-dimensional solids rather than just wireframe or surfaces. This allows for more accurate and realistic simulations of object behavior. So, in the recent years, geometric modeling has continued to evolve with new developments in our areas such as parametric modeling, reverse engineering, and additive manufacturing. Parametric modeling allows users to create and modify geometric models by changing a set of parameters. The reverse engineering allows users to create geometric model of existing objects by scanning them with lasers, scanners, or other devices. Additive manufacturing, also known as 3D printing, allows users to create physical objects directly from geometric model. So, geometric modeling has come a long way since its early beginnings in the 20th century. Today, it is an essential tool for engineers, designers, and artists around the world.
Representation of curves and surfaces. Curves and surfaces are fundamental concepts in geometry and many applications in computer graphics, engineering, and other fields. In this lesson, we will discuss different types of curves and surfaces representations, as well as some examples and more facts. Types of curve representation. Explicit representation. This is the simplest form of representation, where the curve is defined by a function of one or more variables. For example, the circle centered at the origin with radius 1 can be represented by the following explicit function. Number 2. Implicit representation. In implicit representation, the curve is defined by an equation that does not explicitly define the curve's coordinate. For example, the following implicit equation defines the same circle as the above explicit representation. Number 3. Parametric representation. A parametric representation defines a curve by a set of parametric equations, where each equation defines one of the curve's coordinates. For example, the following parametric equations define the same circle as the above explicit and implicit representation. And the last one is piecewise polynomial representation. In a piecewise polynomial representation, the curve is divided into number of pieces, and each piece is represented by a polynomial. This representation is often used to represent complex curves that are difficult to represent with other representation. Here are some examples of piecewise polynomial representation. Bezier curves. Bezier curves are defined by a set of control points, and the curve passes through or near the control points. Bezier curves are often used in computer graphics and engineering to create smooth and realistic shape. B-spline curves. B-spline curves are similar to Bezier curves, but they offer more flexible in terms of shapes of a curve. B-spline curves are also often used in computer graphics and engineering. The last one is NURBS curves. NURBS is an acronym for Non-Uniform Regional B-splines. These curves are generalization of B-spline curves. It can be used to represent a wide variety of shapes, including complex shapes such as ships and airplanes. Types of surface representation. Explicit representation. An explicit representation of a surface is similar to an explicit representation of a curve, but it defines two coordinates instead of one. For example, the following explicit function defines a sphere centered at the origin with radius 1. Implicit representation. An implicit representation of a surface is also similar to an implicit representation of a curve, but it defines 3 coordinates instead of 2. For example, the following implicit equation defines a similar sphere as the above explicit representation. Number 3. Parametric representation. A parametric representation of a surface is similar to a parametric representation of a curve, but it defines 3 coordinates instead of 2. For example, the following parametric equations define the same sphere as the above explicit and implicit representation. Number 4. Piecewise polynomial representation. In this representation, the surface is divided into number of pieces, and each piece is represented by a polynomial. This representation is often used to represent complex surfaces. Here are some examples of piecewise polynomial representation of surfaces. Bezier surfaces. Bezier surfaces are defined by a set of control points, and the surface passes through or near the control points. Bezier surfaces are often used in computer graphics and engineering to create smooth and realistic shapes. B-spline surfaces. B-spline surfaces are similar to Bezier surfaces, but they offer more flexibility in terms of shapes of a surface. B-spline surfaces are also often used in computer graphics and engineering. NURBS surfaces. NURBS surfaces are the generalization of B-spline surfaces. Nerve surfaces can be used to represent a wide variety of shapes, including complex shapes such as ships and airplanes. Example of curves and surfaces. Here are some of example of common curves and surfaces. For the curves, there's line, circles, ellipses, parabolas, hyperbolas, spirals, Bezier curves, B-spline curves. And for surfaces, there's planes, spheres, cylinders, cone, tori, quadric, and Bezier surfaces and B-spline surfaces. Here's more facts. Number 1. Curves and surfaces can be represented in a variety of ways, but most common representations are explicit, implicit, parametric, and piecewise polynomial representation. Number 2. The choice of representations depends on the specific application. For example, explicit representation are more often used in simple curves and surfaces, while parametric representations are often used for more complex curves and surfaces. Piecewise polynomial representation are often used to represent very complex curves and surfaces. Number 3. Curves and surfaces can be combined to create more complex geometry objects. For example, a mesh is a collection of triangles that can be used to represent a variety of shapes. Number 4. Curves and surfaces are used in variety or wide variety of applications, including computer graphics, engineering, medical imaging, and manufacturing.
My name is Angelica V. Dimayuga. Let's talk about the mesh representation and data structure. A mesh representation refers to a computer graphics or computational geometry technique used to represent three-dimensional object or surface. It consists of collection of vertices, edge, and face that define the shape and topology of the object. This representation is commonly used in 3D modeling, computer-aided design, computer graphics, and simulation to represent complex shape and surface. Mesh can be made up of triangles, quadrilaterals, or other polygons, and they provide a versatile way to describe the geometry of 3D object in digital form. A mesh is a data structure used in represent 3D objects by breaking them down into smaller components. Mesh are versatile and can represent complex and irregular shape efficiently. Triangular mesh are commonly used due to their simplicity and ability to approximate any surface. Face define the surface of the object and can be used composed to 3 or more vertices. Mesh can be structured or unstructured depending on the application. Mesh representation typically involves game and simulation. First, vertex data structure. This structure stores information about each vertex in the mesh, including its position in 3D space, normal vector for shading, texture coordinates for mapping texture, and possibly other attributes like color. Second, face data structure. This structure defines how vertices, are connected to form face, triangle, squad, and etc. It is stored in dice or represents to each vertex that make up each face. The choice of mesh representation depends on the specific needs of the application. Triangle mesh are popular because they are simple and widely supported by a graph hardware. However, more complex representation like half-edge mesh offer advantage in certain situations such as topological operation and subdivision surface. A data structure is way for organizing and storing data in a computer memory or storage system to efficiently perform specific operation or tasks. It defines a logical layout for data elements and provide mechanism for accessing and manipulating those elements. Data structure can vary in complexity and purpose, and they are essential for computer programs to manage and work with data effectively. Example of data structure includes arrays, linked lists, stack, queues, trees, and graphs, each designed to specific data management and retrieval needs various computer application and algorithms. Data structure fundamentals component in computer science and programming. They provide a way to organize and store data efficiently in computer memory. Arrays are a basic data structure that store elements of the same time in contiguous memory location. Linked lists consist nodes connected by pointers, allowing for dynamic data storage. Graphs are versatile data structure that represent complex relationship between data points. Hash table use an hash function to map case to value. Enabling fast data retrieval, data structure like heaps are crucial for efficient priority queue implementation.